Okay, so let's get started here. We're going to be working on our notes, or Unit 9. We're going to start with the notes, number 1. Alright, so the first thing we're going to talk about here is what's known as an arithmetic sequence. For these, or basically that means you're adding the same thing over and over and over. So we're going to be working on all these problems here for 1 to complete the notes. Kind of a vocabulary term here, so inductive reasoning is like a pattern. It's kind of the way we're thinking things through. Next, we're going to decide if it's arithmetic. And then we're going to find an unknown term of this sequence. So inductive reasoning is making conclusions based on the pattern you observe. So what's happening each time? A conjecture is a conclusion or an idea you reach using inductive reasoning. Alright, so first looking through these, we're going to find a pattern here. So the first one, a little bit easier to see here, we're actually going to be adding 5 each time. So I could check that by doing 12 minus 7, 17 minus 12. So here we're going to add 5 each time. And that is arithmetic because it means we're adding the same thing over and over. Here, if you do a few different ways of checking, we'll see we're multiplying by negative 2. This one's not arithmetic because we're not adding. Okay. A sequence is a pattern of numbers. Each number in a sequence is called a term. So this is just kind of vocabulary to use here. Big one is an arithmetic sequence is a number sequence where you add a fixed number to each previous term. So we add the same thing over and over, whether it's positive or negative. Moving on down a little bit here. So the blank is the name for the fixed number you add to each previous term in the arithmetic sequence. This is what's known as the common difference. The variable we're going to use here is d. So we're just going to write a d to represent that variable. Alright, for these ones, we are going to determine if the following sequence is arithmetic. If they are, identify the common difference. So, the way to figure that out, we're going to do second minus the first term, and third minus the second term. So we're just going to check to make sure we're doing the same thing over and over. So for that, the second term minus the first term, so I'm going to do 83 minus 100. For that calculator, we get negative 17. Third minus the second, so third term, so that's 66 minus 83. Here I also will get negative. Let's check here. Again, you can use GeoGebra for these calculations. Negative 17 again. So, since I found the same number twice, my d is equal to negative 17. And yes, it's arithmetic. Because we're doing that same thing. We're adding negative 17 each time. Here, second minus the first, third minus the second. These numbers aren't the same when I did second minus first and the third minus the second. So, it's not arithmetic. And if it's not arithmetic, we don't have a d. So doing that first step there each time is going to be our thing we're going to do every single problem. Alright. An explicit formula allows direct computation of any term for a sequence. So here's our explicit formula. It's going to look kind of like this. We'll kind of skip over this one for now. And let's take a look here. This is going to be our kind of go-to format. So, an is the nth term in a sequence. So if I had a with a little 2, it would be this a sub 2, or the second term. a1, that's the first term. in a sequence. D we kind of referenced earlier, that is the common difference. So what we add or subtract each time. N is the number of given term. So it's the same N we see here, except we just go ahead and put it into the problem. Alright, for these, we are going to identify the first term, common difference, and the term number given the explicit formula for the following arithmetic sequences. I want to find these terms. Alright, so here, our first term, so A1, that's what's out front here, that's 2. Our D is 3. Moving on a little bit here. Notice that n minus 1, that's going to be a constant in this form. That's just always kind of there. So just be used to it. So A1 and D are what changes. Here, A1 is negative 5. And our D, since it's minus 7, would be negative 7. Now, when we're finding these terms, essentially we're plugging this in for n. So A sub 2 for the second term would be 2 plus 3, parentheses, 2. So notice these numbers are the same, minus 1. For the seventh term, A with the 7. So now instead of a 2 there, I have a 7 and the 17. We'll go through calculating these in a minute. Writing them out over here for the same terms. So that negative 5 is always going to be our starting point. Minus, 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 7, 7, 7. Now what changes each time is our n. So here my n is 2, here it's 7, and here it's 17. And then our minus 1. Now, for calculating these, we're going to use GeoGebra just like we've talked about before. Let's go ahead and X out of this thing. So go ahead and open up your GeoGebra. So all of your GeoGebra should look the same whether you finished Unit 1 or not. We went through as a class on how to set this up. So here we're going to go ahead and do a little bit of math. So I'm going to type these in just how they look. So 2 plus 3, parenthesis, 2 minus 1. Sorry about that. Changing my laptop around. So we had 2 plus 3, parenthesis, 2 minus 1. So in my input bar, 2 plus 3, parenthesis, 2 minus 1. And we get our answer. So it shoots out my 5. Key idea is you have to put those parentheses in there. Otherwise, it will do it in the wrong order. For our next one, same 2 plus 3, 7 minus 1. 20. And 2 plus 3, 17 minus 1. Actually, click on that. So again, 2 plus 3, parentheses, 17, minus 1, add it, and we get 50. With our other ones here, so again, we type it just how it looks. Negative 5 minus 7, parentheses, 2 minus 1. Negative 5 minus 7, parentheses, 2 minus 1, negative 12. And you can go ahead and find the rest of those answers following that same formula. Here, we'll be doing the exact same thing. Just kind of, again, finding that common difference, seeing if it's arithmetic. So if you'd like, you can go ahead and complete these now for practice. But again, it's the same thing as we've done up here. Once you finish that, what you're going to go ahead and go on to here is number 2. For this one, you guys are going to go ahead and complete all of these problems. So for these first ones, determine if the sequence is arithmetic. If it is, find common difference, so D. Down here, we're going to go ahead and identify the common difference, and we're going to find the 52nd term. So here you can just focus on finding that 52nd term. And once you've completed that, you can go ahead on here to 3. So this is going to be another section of notes here. Alright, so again, kind of a review, that's what our formula looks like, which we just talked about. We're going to skip the old way for right now. I'm just going to focus on the new way. So, write the explicit formula for the sequence below. Find the 37th term. Alright, so to find it, first we got to find D. And the way to do that is, again, second minus first, and third minus second. So this is checking to see if we can even do it, if it is arithmetic. This gives me 2, this gives me 2. So, since I have that common difference, it's the same each time, this is indeed arithmetic, and I can say that D is equal to 2. Now, whenever we're given a sequence of numbers, our first term here is always going to be our A1. So, if I want to write the formula for this, I know it's going to look like AN is equal to A1 plus D n minus 1. So, plugging in our A1 and our D, that gives me A sub n is equal to 12 plus 2 n minus 1. And again, had this D been negative, then this would be minus 2 instead of plus 2. Alright, so if we want to find some of these terms, it's just plugging in. So if I want to find 1, I would plug in 1 for n. That would give me 12. And again, that's just typing into GeoGebra just like we did in the previous lesson. For 2, I'd plug in 2 for n. That would give me 14. Plugging in 3 for n, that would give me 16. Plugging in 4 for n, that would be 18. And for 37, let's go ahead and do 12 plus 2, parenthesis, 37 minus 1. So 12 plus 2, parenthesis, 37 minus 1. Jumps all the way up to 84. So again, plugging in should look familiar from before. We'll go ahead and skip over this part. Alright, for this one. Oh no! You broke the screen on your cell phone and now you are saving money to purchase a new one. You want to purchase the new Samsung Galaxy Note 3. But unfortunately, you have to pay the full price for the phone. So no payment plans here. You have 175 saves so far and plan on saving 20 per week. So for our explicit formula here, let's see, we started with 175. So our A1 is 175. And if I'm going to save 20 each week, that tells me my D is a positive 20. So our formula, it's a positive D, so I can put plus there. And the n minus 1 is just like our x. It's like our variable, so it's always going to be in 10 weeks. So here they're saying plug in 10 for n. So this would be A sub 10 So GeoGebra 175 plus 20 parenthesis 10 minus 1. $355. So in 10 weeks we'd have $355 saved. If the phone costs $700, how many weeks? So what that's saying is this time it's given like our end goal. So 700 is equal to 175 plus 20 and minus 1. So solving this one, that's our formula. So to solve it, I would subtract my 175 from both sides, which would give me 525 is equal to 20 times n minus 1. 20 is on the outside, so what we can do is go ahead and distribute a bit here. So I would have 525 is equal to 20n minus 20. Add our 20 to both sides. So I get 545 is equal to 20n. Divide by 20. So 545 divided by 20. 545 divided by 20. 27.25. Oops. So here, n equals 27.25. So that's about how many weeks it would take us to purchase this phone. Alright, working through here. This is just writing the sequence like we did above. Here's more of an application problem. So I'm just going to go ahead. I would say pause the video right now and go ahead and try these problems. What I'm going to do is go ahead and just work through these real quick here. So that would be the stuff you should get there for the first one. Here, it will cost $50 to park the bus and $87.36 per ticket. So that's like my D here. This is my A1. So I know it's going to cost me at least $50. So that's my A1. And then I'm going to add on that cost of $87.36 for every ticket. So an N minus 1. For 42 here, we just plug in 42 for N. So A42. And for this one, we're given a total. I want to figure out how many people can come. So this would be like the one above where we worked a bit backwards. So it would be 25,000. N minus 1. So this time you would go ahead and reference up here. Same steps, how we solved for N. Once you've completed this, you guys are going to go ahead on to number 4. And go ahead and work through this practice. So here, you're going to go ahead and write the explicit formula and then find that term. So for this one, I would want your A sub n and whatever A28 is. And that'll change up a bit for each problem. Down here, you're going to complete each thing, so you're going to write the formulas first. And then go ahead and solve our problems. So with that, this would be your guys' next set of practice. Next thing we're going to move on to is another section of notes, number 5 here. So we're going to go ahead and skip over this first page here and go right on down to geometric sequences. So geometric sequences are a bit different from what we've seen with arithmetic. Essentially, it's the same concept, just a different formula. So for here, we're going to go ahead. You can think of it as the dividend. Basically, it's like when we divide numbers. So it's what we're multiplying by each time. And for this one, we're going to use the variable r. So this is what's known as the common ratio. So A sub n is still going to be the same thing, nth term in a sequence. A1 is still that first term, so nothing's changed so far. N is still the number of a term. So the only thing that's different here is R. So D was the common difference. This is what's known as the common ratio for R. So the common ratio can be found by dividing any term by the preceding term. So dividing the first one by the second by the first, third by the second. So that same pattern. So we're going to determine if they are. So again, following that same pattern, second term. This time we're divided by the first term. Here, second term divided, or third term divided by the second term. So that same pattern we've seen with arithmetic. Here we get 6. Here we also get 6. So since they're the same, yes, it's geometric, and r would just be equal to 6. Over here, if I check, so second divided by the first, third divided by the second. So 912 divided by 91. We get about 10.12. Nine one two two divided by 912. This one's just 10. We notice they're not exactly the same. They're pretty close though. But since they're not the exact same number, no, it's not geometric. So we don't have a common ratio. Alright. Example 2. Makers of Japanese swords in the 1400s repeatedly folded and hammered the metal to form layers. The folding process increased the strength of the sword. The table below shows how many the number of layers depends on the number of folds. I'm going to write the explicit rule for the geometric sequence described by the table. Alright, so step 1, find that common ratio. So here we're looking at our number of layers, and we're going to divide each time. So only looking at this one to get our ratio. So 4 divided by 2, 8 divided by 4. We check, that's 2, this is also 2, so this is geometric. And our ratio is just 2. A1 is that first term we get. So ignore all these ends. So A1 is just going to be 2. So here it's A sub n is equal to 2 times, back up at our formula here, A1 times R up to in an exponent n minus 1. So 2 times R is 2. I like to put parentheses around R, it just makes it look a little nicer. And then up here in the exponent, n minus 1. So the key idea there, that n1 is up in the exponent. So working through this one comes from a graph, but the data is still the same. So here, we're going to kind of ignore all our x values, and we're just going to be looking at those y's. So completing the table, at 1, I'm at 100. 2, I'm at 80. 3, I'm at 64. Give me a second, guys. My computer's being a bit buggy. Okay, my apologies. Got a little crust up there. So again, just kind of copying down our numbers there. We had 180, 64. Give me a second while I try and fix this page. Okay, so for some reason, it's not letting me write here, so I'm just going to kind of walk you guys through this one. So each of these numbers is going to go with these next terms. So 180, 64, so on and so forth. I'm going to show the work here to the side. So finding if it's geometric, we're doing the second y value divided by the first, third y value divided by the second. So for part B, I'd be doing 80 over 100, and then 64 over 80. So we get 0.8 and 0.76. Those are not exactly the same, so it's not geometric. Therefore, we cannot even write an explicit rule. Moving on down to here. Here we got some practice problems, right? So we're going to go ahead and look at a couple of these. What you're going to go ahead and do here is just work through each of these. So the big ones I want you to focus on here. This page is obviously exempt, it's just a blank one. Let's work through all 4 of these problems. So here I would do 9 divided by 1, 25 divided by 9. You could check in a calculator. Those are not going to be the same number, so this one's not geometric. Here I'd have negative 20 divided by 4, and 100 divided by negative 20. In both these cases, we'll get negative 5. The negative is important. So again, keep that r at negative 5. So this one would be geometric. Kind of the same thing here. We're just given the problems in a bit of a different format. Here, reading from the graph, so our FNs would be 128, 64, 32, and 16. So we'll skip over this one for now. You can complete it, but we're just going to go ahead and do this one. It's kind of the same thing. So is it geometric? I'm checking. Second term divided by the first term. That's going to give me 0.5. Third term divided by the second term. I also get 0.5. So yes, this one is geometric. And in fact, r is equal to 0.5. Or if you want it the fraction like we've seen before, you can write it as 1/2. The explicit rule, well, here's my a1. It's the first term. So it would be an is equal to a1 times, in parentheses, you can either write that 0.5 or you could leave it as 1/2. Either way is fine. Up to the n minus 1. So from this point, once we've gotten through our notes here, you're going to go on to number 6. And you're going to be completing all of these problems. So for our first ones here, check if they're geometric. If they are, find that common ratio. Find the first 5 terms in the 8th term. So for each of these, we're going to be finding a1, a2, a3, a4, a5, and a8. So we're just going to go ahead and plug those numbers in for n and write this in GeoGebra exactly how it looks with those parentheses. Here we're working a bit backwards, so we'll go ahead and do one of these together. So let's do you know what? Let's go ahead and skip these. So we're going to skip 11, 13, 12, and 14. Moving on down here. Given the first term and the common ratio, find the first 5 terms and the explicit formula. So here you're just going to go ahead and write out your a sub n, and then you're also going to find that a1, a2, a3, a4, and a5. So just plugging in what we're given into our formula, and practice typing it into GeoGebra. As far as GeoGebra goes, to get the up to symbol, so to get it up in the exponent, let's say I want to do 5. To get the times, hold the shift key and press 8. That gives me my multiplying. And let's say I had an r of 0.5, and I want to go up to n minus 3. So let's say I had my n was 10. So to get up to, you're going to hold the shift key and press the number 6 to get that up arrow. The key idea here is you have to put this whole thing in parentheses. So if I want to, say my n was 10, then it would be parenthesis 10 for n minus 1. It has to be like this in parentheses. So this is kind of the general form you can use for every one of these. Press enter. And here I get something really, really small. But again, I typed it incorrectly. So make sure you're typing those in with that method. We're going to go ahead and skip over these. And these. As well as all these. So pretty quick assignment. So you're just doing the ones that we didn't cross out, essentially. Alright, moving on to number 7. What we're going to do here together is going to be kind of the first half of this thing. So we're going to kind of skip around here. I'm going to do some, and you guys will complete the rest. Okay, so first question here. Looking at the key characteristics of a basic exponential function. In an exponential function, the exponent, or the variable, is an exponent. So our variable is up in there. It's up here. So b is just going to be some number. B is a base. So it's basically any real number greater than 0. So it could be 1, 10, 1.2, 8.9, a fraction, as long as they're positive, and it's not 1. Alright, so here, I'm just going to show you guys exactly how to type these things in. So we're given the graph of 2 to the x. So I'm looking at 2 up to the x. So when I plug these in, it would be 2. Now I'm going to type this how it's going to look in GeoGebra. Up to, parenthesis, negative 3. So I'm just going to go ahead and write all of these out the way we're going to type them into GeoGebra. So I'll do the first few with you guys. So 2 up to the negative 3. I'm going to get rid of all this stuff just so we're not confused. So 2, to get the up to again, shift 6, parenthesis, negative 3. If you don't put those parentheses, GeoGebra is going to be very upset with you. It won't give you the right answer. Press enter. I get 0.13. Let me just check that real quick. I may have hit the wrong key there. Oh, we're all good. So ignore that. Definitely was right the first time. So here we get 0.13. 2 up to the negative 2. I'm going to do the next few here. So we kind of see our pattern. 0.25, 0.5, 1. And you could check the rest of those as well. So as far as graphing this goes, well, at negative 3, I'm at something really, really small. So I'm somewhere down here. Negative 2, a little higher. Negative 1, kind of halfway. At 0, I'm at 1. At 1, I'm at 2. 2, I'm at 4. And at 3, I'm all the way up at 8. So what our graph would look like here is something like this. Another way we could look at this graph, we're going 2 up to the x, is if I went back to GeoGebra, this is our graphing panel. So here, I can go to my input and type y equals 2 up to the x. Click enter. And once we click it, you'll see over here we get a pop that says function. It just names the function. It might be f, it might be j, a, whatever it is. It'll name it and the equation. So y equals 2 up to the x. And this can actually graph it for us. So we can kind of see here, well at 2, I'm up at 4. If we zoom in a bit, which you can just do with your fingers kind of dragging into the screen, so just like on your phones. So again, our graph here looks the same as what we've generated here. So this question is x increases, f of x. So we're saying as x gets bigger, it goes up. So f of x also increases. As x decreases, so as it gets smaller, we're going down. So also decreases. For this one, it's not going to ever touch the x-axis. We can kind of look visually here. GeoGebra does a bit of a better job. So even as we move to the left here, it gets really, really small, but if you zoom in, it's never going to touch it. Because that's just, again, part of the exponentials. They don't cross that x-axis. Domain and range, here we look. So we go up forever. So my domain, since I'm going to be having any x's and any y's, there's nothing that doesn't work. It's just going to be all real numbers. Because, again, we go to the left and right forever. For the range, it goes up forever. So I'm going to go towards infinity. But you see I never cross that 0. So for my range, it's going to be from 0 to infinity. For domain, you could also just do this like cool R. That stands for all real numbers. Here, we have a new function. So it's 1/2 to the x. So how we would type this in GeoGebra. Parenthesis 1 divided by 2 up to negative 3. So notice here, I'm writing it with parentheses. I need to keep those in there. So everything is getting parentheses. Now the reason why I'm putting them around the base this time is because it's a fraction. If it's a whole number like we did in the first one, you don't necessarily need them, although putting them in there does not hurt. So if we go ahead and calculate these out, again, you can use GeoGebra for this. So checking that 1/2 up to the 0, let's say parenthesis 1 divided by 2 up to 0. Definitely still 1. So my bad there, I accidentally wrote 0. So this would be 1. 1/2 to the negative 1. Check with GeoGebra. So plotting this one out, at -3, I'm up at 8. So it kind of makes our graph look a little backwards here. So this time, as x increases, meaning as I'm going to the right, it's actually going to go down. So it's decreasing. As it decreases, so as I go to the left, it's going up. So that means it's increasing. The easiest way to tell with these, if it's asking decreasing, increasing, is just to graph it in GeoGebra. So I'm going to go ahead and delete that one I have here in all these numbers. And I'm going to type our new one. So we got y equals parenthesis 1/2 up to the x. Press enter. Looks right, so it formats it nicely. And we see here this is the same graph we got. So as I go to the right, it's going down. So as x increases, or goes to the right, it's decreasing. As x decreases, as I go to the left, I see I'm going up, so it's increasing. Domain and range, we're always going to have the same thing here. So for our domain, it's going to be all real numbers. In range, I don't cross 0, but I go up forever. So it's the same thing going to infinity. We're going to go ahead and skip these. So end behavior just kind of talks about what we talked about up here, increasing versus decreasing. And again, you can just tell that from looking at the graph. So we're going to go ahead and skip over these ones. And these. And those. What we're doing here, we'll talk about these briefly here. Basically, if it's less than 1, so if your base, or the number here is less than 1, so b, if it looks like this, so f of x, b up to the x. If b is less than 1, it's going to be what's known as decay. So it's going to go down from left to right. If b is greater than 1, it's growth. So so this one would look something like this, whereas here, we're going to be going up. So down from left to right, up from left to right. So decay means it's less than 1, growth, it's more than 1. What I want you guys to go ahead and complete now, as far as your practice goes here, I want to be 9 and 10, and you're going to identify whether it's growth or decay. And for our last bit of this unit, we're going to go to number 8. So here we have an A out front. I'm going to give you a hint, this one's going to go pretty quickly because it's essentially the exact same thing. So, let's see what we got here. So we're going to kind of skim through these notes real quick here and then get to the practice at the bottom. For these first ones, basically we're just going to go ahead and plug these into GeoGebra just like we've done before. So again, keeping the parentheses the same, here's how I would type this one in. So I would do 2 times parenthesis 3 divided by 4 up to, and then each of these numbers for x. So if I want to do -2, GeoGebra, answer. So not a whole lot different here. Decimals, same thing. So this would be 0.9 times 0.6 up to, if I want to do -3, -3. GeoGebra, answer. So not a whole lot different there. Again, Same thing here, this is just typing stuff into GeoGebra, so we should be able to complete these. Here's just some more visuals, so the growth going up, decay going down. Alright, so finding these things. So what we're going to do for our notes is go and complete this page, and then everything below it is going to be your homework. So you're going to work on numbers 1 through 5 for the homework after we complete these notes. Alright, so let's take a look up here. So, growth is 1 plus r, decay 1 minus r. So we're going to keep it as a decimal here. So, for this one, 8% growth. That means I'm doing 1 plus, well 8% is a decimal, I do 8 divided by 100, get 0.08. So whenever you need to take a percent to a decimal, you always divide by 100. Again, that's like a note card piece of information. So here, my base would be 1.08. Decay would be 1 minus. 23 divided by 100 gives me 0.23. And that's going to give me 0.77. So my base here, 0.77. For these ones, a decay would be minus. And a growth would be plus. So again, getting those decimals as this. Alright, let's get into some problems here. So, you just invested $10,000 at the bank. The bank has an annual interest rate of 0.0005%. How much money do I have in 15 years? So first, let's think about our formula here. So, the way we've been writing these looks kind of like this. So A times their base, B, up to the X. So A here represents how much we start with. So I started off here with an investment of $10,000. To figure out my base, so let's say I invested money, and I'm making money. So that means I'm going to be adding. So it's 1 plus. Now, this is tricky. They did put a percent here. So first, I'm going to divide that number by 100. So for my R, my rate that's changing, always remember you divide it by 100 first. So that is what we're plugging in here to find our base. So our base is there. So for my equation, y equals A times our base up to the X. For this next part, how much money am I going to have after 15 years? We're going to go ahead and plug that in because X is how many years, Y is our money. So it would be 10,000 times our base up to the 15th power. Let's go ahead and use GeoGebra here. I'm going to go ahead and delete this. So 10, 1, 2, 3 times. And outside those parentheses up to the 15th. So $10,007.50. So that's how much money we have after 15 years. Situation 2, biology class. You are studying bacteria that is in a petri dish. You know that there are 600 bacteria present in the dish initially, and the number increases by 200% every 15 minutes. So, for this one, our A is how much I'm starting with. So I know I got 600 that I'm going to start with. For my B, well, 200%, so 200 divided by 100 gives me an R of 2. So it's increasing, so 1 plus 2 is equal to 3. Now, I got Y equals, plugging in over here, A is 600 times our base up to the X. Now, kind of a trick with this problem. We're talking about minutes. So every 15 minutes this thing happens. So after an hour, well, let's see, there's 60 minutes in an hour. and this thing happens every 15 minutes. So I want to figure out how many times 15 minutes happens in 1 hour. So I would divide. So that tells me this thing's going to happen 4 times. So to figure it out, I would plug in 4 for my x. GeoGebra, answer. After 3 hours, let's see, we got the same equation we're starting with. Now I got 3 hours. Well, okay, so there's 60 minutes in 1 hour, but I want 3 of them. So that tells me I'm looking at 180 minutes. And then to figure out how many times 15 minutes happens in 3 hours, I would divide by 15. So I would get 12. Again, GeoGebra for the calculations. So I would be plugging in 12 to this problem. GeoGebra, we get our answer. So to finish up your practice for this unit, what you guys are going to be working on, as I said earlier, are the numbers 1 through 5. Take your time on these. Go slow. Make sure you're asking if you need help with anything. Pay attention to whether they're growth or decay. Once you've completed that, the last thing you have to do for this unit is complete the review. We're looking at all these questions. And when you're done, again, check it in with me. And then the last thing you got to do is go ahead and let's pass that unit exam.